Hello everyone. Welcome to the week 5 of the problem solving session for the course Differential Equation for Engineers, which is taken by Professor Srinivasa Manam at IIT Madras. And I am Priyanka Agarwal, PMRF scholar at Chemical Engineering Department at IISc Bangalore, and I am going to take these tutorial sessions. So let's begin with the problems. So we will solve a problem related to Legendre polynomials. So the first problem is that show that the Legendre's polynomial satisfy the following. And the equation to satisfies 2n plus 1 Pn of x equals to p dash n plus 1 x minus p dash n minus 1 x. Okay. So solution from Roderick's formula. What we know is how Pn, that is the Legendre polynomial, is defined. So Pn of x is equal to 1 by 2 to the power n into n factorial d to the power n over dxn. So dn by dxn x square minus 1 to the power n. So this is the definition of Pnx from Rodriguez formula, where x belongs to any real number. Now Pn dash x can be written as d by dx of Pnx, right? So what will it be now? This will become 1 over 2 to the power n into n factorial, and now we differentiate this entire thing. So this is now t n plus 1 over dx n plus 1 x square minus 1 to the power n. Now what will this be? 1 over 2 to the power n into n factorial, and this we can write it as d by dx. So n times differential over d by dx of x square minus 1 to the power n. So what will this become? 1 over 2 to the power n into n factorial dn by dxn. Okay, so when we differentiate this, what will it be? N times x square minus 1 to the power n minus 1. Now differential of x square minus 1, which is 2x. So this is what it becomes. So we can write it as 2n, we can take outside, 2n over 2 to the power n into n factorial dn by dxn, or x into x square minus 1 to the power n minus 1, right? Now can write this as 1 over 2 to the power n minus 1 into n minus 1 factorial, right? So this will be now d by dx to the power n minus 1, and we differentiate it once again. So this is now x square minus 1 to the power n minus 1. As such, x differential is 1. Now x remains and we differentiate those. So this becomes n minus 1 x square minus 1 to the power n minus 2 into 2x, right? Okay, so what can we write this as? 1 over 2 to the power n minus 1 factorial d to the power n minus 1 over dx to the power n minus 1, and this will become, you can take x square minus 1 to the power n minus 2 as common. Now what will remain is x square minus 1 from here. Now what will be remaining here? Plus 2x square into n minus 1. Okay. So yeah, this is what we have now. Now if we just expand this term, open this term, what will it be? X square minus 1 plus 2mx square minus 2x square, right? Okay, so this you can write it as minus x square minus 1 plus 2mx square. Okay, so we can take x square as common and write it as 2n plus 1, and this will be there minus 1. Alright. So what Pn dash of x becomes? It is 1 over 2 to the power n minus 1 n to n minus 1 factorial into d by dx n minus 1 x square minus 1 to the power n minus 2. Okay, it will be minus sign here, but it will not be minus sign. Yeah, so this is minus x square if we take common. Let's take x square as common. So this will be 2n minus 1. Square minus 1. This is 2nx square minus 2x square. 2 into minus x square minus 1 plus 2x square. We take x square as common, then this becomes 2n minus 1, and we have a minus 1 there. x square 2n minus 1 minus 1. Okay, if you see this term, you can also write it as 2n plus 1 minus 1, because this will be 2n plus 2 minus 1, which is 2n minus 1. Okay, so let's open it in that way. 1 over 2 to the power n minus 1 into n minus 1 factorial d to the power n minus 1 dx n minus 1 dx square minus 1 n minus 2. Here, if you write it like this, then you can write it as 2 n plus 1 minus 1 x square minus 1. Okay? Let's see what this means. If you just look at this term. Okay, so let this be this only 2n dash x, and let's call this as the first equation. Now let n equals to n plus 1. So this will become 2 dash n plus 1 x equal to 1 over 2 to the power n minus 1. So this will be now 2 to the power n, because this is replaced, into n factorial dn over dxn. This will become x square minus 1 to the power n minus 1, and what will this become? 2 into n plus 2 minus 1 x square minus 1. Right? So what will this be now? 1 over 2n into n factorial dn over dxn into x square minus 1 to the power n minus 1, and write it as so we can write it as x square into 2n plus 1 minus 1. Now, similarly, we can write p dash n minus 1 x, and this will be 1 over 2n minus 1 to n minus 1 factorial.
ಮೋಸ್ಟ್ಲಿ ಎಲ್ಲ ಲಿಂಕ್ ತಪ್ಪ ಹೋಗಿರ್ತದೆ ನಿನಗೆ.
So this will be so this is now x square minus 1 to the power n minus 1. So this is what we have is t n minus 1. Now what will be p dash n minus 1? This will now become 1 over 2 to the power n minus 1 into n minus 1 factorial d. So we have to differentiate it d by dx. Now this becomes differential n times. x square minus 1 to the power n minus 1. So now can write this as 2n divided by 2. That 2 can be taken in the numerator, and this is 2 to the power n. If we multiply by n in both numerator and denominator, this is 2n, and this will become n factorial. So this is now dn over dxn x square minus 1 to the power n minus 1. This is our equation 2. And let's call this as equation 1. And it's not called as an equation. Okay, now we have to do equation 1 minus equation 2. What will that be? P dash n plus 1 minus P dash n minus 1. So what will that be? So we have this 1 over 2n into n factorial is common, and dn over dxn. There we have this x square minus 1 to the power n minus 1 that we can take common into, and first becomes x square into 2n plus 1 minus 1, and from here it comes minus 2n. So this can be written as 1 over 2 to the power n into n factorial dn over dxn, and this is now x square minus 1 to the power n minus 1 into, we can write this as 2n plus 1 x square minus 2n plus 1, right? What will it be now? 1 over 2 to the power n into n factorial dn over dxn, and we can write it as x square minus 1 to the power n minus 1 into 2 plus 1 is common, then this becomes x square minus 1, and therefore we can write it as 1 over 2 to the power n into n factorial d by dx and x square minus 1 to the power, now this becomes as n into 2n plus 1. So I can take 2n plus 1 outside, 2n plus 1 over 2 to the power n into n factorial dn over dxn into x square minus 1 to the power n. So this, what is this? This is Pn of x, right? So now what we have is P dash n plus 1 x minus P dash n minus 1 x equals to 2n plus 1 over 2 to the power n into n factorial Pn of x. So, this will also be part of this. this was the equation relation which we wanted to prove, and this is we have derived. Hence, good. Any doubts in this before we move on to the next question? Okay, if not, let's move on to the next question, where we have to find the radius of convergence. Of the following series. Okay. So the first series is e to the power x, which is summation n summation n equals to 0 to infinity x to the power n over n factorial. And this can be written as 1 plus x square by 2 factorial plus x cube by 3 factorial and so on till infinity. So now our task is to find the radius of convergence of this particular series. Okay. So e to the power x is written as summation n equals to 0 to infinity an x to the power n. If we could see these two, what is an? An can be written as 1 over n factorial. Similarly, an plus 1 can be written as 1 over n plus 1 factorial. Now, how do we define radius of convergence as 1 over limit n tends to infinity an plus 1 over an. So this is how we define radius of convergence. What will this become? 1 over limit n tends to infinity n factorial over n plus 1 factorial, right? And this can be written as 1 over limit n tends to infinity 1 over n plus 1. So this becomes 1 over limit n tend to infinity 1 over n plus 1 would be 1 over infinity, that is 0, almost 0, and we can write it as infinity. So what the radius of convergence is? It's infinity for this particular case. Okay, any doubts in this? Okay, if not, then let's see the second series for which we need to find the radius of convergence, that is 1 over 1 minus x equals to summation n equals to 0 to infinity x to the power n, and this can be written as 1 plus x square and so on. Okay, so now similarly for 1 over 1 minus x, if we write it in the series form, what are the values of coefficients? In this case, the coefficients are 1. So all the coefficients are 1 in this case. So the radius of convergence will now be 1 over limit n tends to infinity a n plus 1 over a, right? And this is 1 over limit n tends to infinity, 1 over 1. So this is 1. So for this case, radius of convergence is equal to 1. Okay. Any questions on this? Before we move on to the next topic as such, that is the Frobenius method, are there any questions? Okay. Briefly, I will discuss the Frobenius method so that we can solve a problem related to that. So this is just for recap. Already this has been taught in lecture in detail. Okay. So now let's look at the Frobenius method for second order equations. Now let's say if the differential equation is phi double dash plus p of x over x minus x0 y dash plus q of x over x minus x0 square into y equals to 0. Let's say this differential equation has a regular singular point at 0. Okay, so we have seen the power series expansion for ordinary points. Now Frobenius method is useful when we have a regular singular point. So now let's say that this particular differential equation of second order has a regular singular point at x0. So then that would mean that this px and qx are analytic about x0. Okay, so that's the because it's a regular singular point. Now if they are analytic about x0, we can expand this px and qx in Taylor series about x0. Therefore, we can write this p of x as summation n equals to 0 to infinity pn x minus x0 to the power n, and qx as we can write this summation n equals to 0 to infinity qn x minus x0 to the power n. Right? So let's call this equation 1, equation 2 and equation 3. Now we can substitute equation 2 and 3 in the given equation 1 and obtain a series solution, that is Frobenius series solution. Okay, so substitute equation 2 and 3 in the given equation 1 to obtain a solution yx in the form of Frobenius series. Okay, so okay, so before I move further, let's recap what the Frobenius series is. This is y of x can be written as x minus x0 to power k summation n equals to 0 to infinity a of n x minus x0 to the power n, where we call this k as initial exponent, and we do not have to take a naught as 0. So a naught should always be not equal to 0. And how can we make sure that a naught is not equal to 0? By ensuring a proper choice of k. So this is ensured, which is ensured by a proper choice of k. Okay. So this is Frobenius series. Okay, now going back, now when you substitute the value of px and qx in the given equation to obtain the solution yx, and how do we obtain the solution yx? Is by equating the coefficients. Equating the coefficients of x minus x0 to the power n plus k minus 2 for n equals to 0, 1, 2 and so on. Okay, any doubts in this question? If not, then we will solve our question and see how to apply this Frobenius series solution. Okay, so let's move on to the question where we have to find the solution using Frobenius method. Okay, and the given equation is 4x y double dash plus 2y dash plus y equals to 0. Okay, now first we have to check which is the singular point and whether it's regular singular or not, and then we will apply Frobenius method around that particular singular point. Alright? Okay, so if we write this equation in the standard form, what will it be? Y double dash plus 1 by 2x y dash plus 1 by 4x y equals to 0. So clearly from these two, what we can say is that x equal to 0, there is a singularity. So x equals to 0 is a singular point. Now we want to know whether this singularity is regular or irregular about x equals to 0. Okay, so let's see for this. So limit x tends to 0, this 1 by 2x into x minus 0. What will it be? 1 by 2. So what is this? This is limit is finite and it exists. So this particular function is analytic. Now let's check the other part. Limit x tends to 0, 1 by 4x, and this is x minus 0 whole square. Now what this becomes? Limit x tends to 0, x over 4, and this is 0 again. This is final when limit is existing. So therefore we can say that x equals to 0 is a regular singular point. So we have done several questions in the last tutorial to find whether the point is a singular point, ordinary point, it's regular singular or irregular singular. Now once we know that x equals to 0 is regular singular point, now we can apply the Frobenius method. It's a mistake. Okay. Now to solve using the Frobenius method, let's consider the solution of the form. Let the solution be y of x equal to mod of x to the power k summation n equals to 0 to infinity Cn x to the power n, where k is an unknown scalar, right? And all the Cn's are also unknown scalars. Okay. Now for x greater than equal to 0, what we can write? Mod of x to the power k as x to the power k. So the solution yx becomes x to the power k summation n equals to 0 to infinity Cn x to the power n. Now y of x becomes summation n equals to 0 to infinity. You can take this inside. Cn x to the power n plus k. Now if we differentiate it once, y dash x will be summation n equals to 0 to infinity Cn into n plus k into x to the power n plus k minus 1. And what y double dash x will become? It is summation n equals to 0 to infinity. Now we have to differentiate this. So n plus k, it's already here. And now another term will come n plus k minus 1. And coefficient Cn, and this becomes x to the power n plus k minus 2. Now you have yx, y dash x, y double dash x in series form, and we place it in the given equation, this one. Okay. So you have to do substitution. So the original equation is 4x y double dash plus 2y dash plus y equals to 0. Now we substitute, what will it become? 4x summation n equals to 0 to infinity n plus k into n plus k minus 1, right? Cn x to the power n plus k minus 2. Okay. I hope that's straightforward. And then it's 2y. So 2 summation n equals to 0 to infinity Cn n plus k into x to the power n plus k minus 1. And then y, which is summation n equals to 0 to infinity Cn x to the power n plus k. Okay, this is equal to 0. Okay, so we have substituted. Now, so this 4x is there. Now this x can be multiplied to this, and this will become n plus k minus 1. This is also n plus k minus 1. Right? So let's rewrite it. Summation n equals to 0 to infinity 4 n plus k n plus k minus 1 cn x to the power n plus k minus 1, and this will become summation n equals to 0 to infinity 2 n plus k cn x to the power n plus k minus 1 plus summation n equals to 0 to infinity cn x to the power n plus k equals to 0. Now these terms can be combined. So what will it be now? Summation n equals to 0 to infinity 4 n plus k into n plus k minus 1 plus, from there it comes 2 n plus k cn x to the power n plus k minus 1, and then we have this y term n equals to 0 to infinity cn x to the power n plus k equal to 0. Okay, now let's simplify this. We can take n plus k as common, right? And what will this be now? 4 n plus k minus 1. So minus 1 plus 2. Okay, so this is this. So this can again be written as n plus k into 4 n plus k minus 4 plus 2 will be minus 2, right? So we can write this as summation n equals to 0 to infinity n plus k into 4 n plus k minus 2 cn x to the power n plus k minus 1 plus summation n equals to 0 to infinity cn x to the power n plus k. Okay, now we have to equate the coefficients of x powers, all the powers of x to 0, because we have some coefficients here but it's 0 here. So for doing that, we have to first make this equal. How can we do that? So this is n plus k minus 1. If we replace n by n plus 1, we can do that. But what will this become then? If we replace n by n plus 1, this will now then start from minus 1. So n will start from minus 1 to infinity, and this becomes n plus k plus 1 into 4 n plus k plus 1 minus 2 cn plus 1 x to the power n plus k, and this term is also now summation n equals to 0 to infinity cn x to the power n plus K2. This is equal to 0. Now let's expand this, the n equals to minus 1 term, and then what we will have is the 0 to infinity. So if we just substitute n equals to minus 1 here, what we will get is k into 4k minus 2 c0 and x to the power k minus 1, right? And then you can write all the terms combined as summation n equals to 0 to infinity. Let's combine both these terms. So this is now n plus k plus 1 into 4n plus k plus 1 minus 2, and this entire thing will have a coefficient Cn plus 1, okay, and this has coefficient Cn, and this is equal to 0. Okay, so from this term what we can get is differential equation. Since C0 cannot be 0, then coefficient of x to the power k minus 1 has to be 0, and C0 cannot be 0, therefore k into 4k minus 2 has to be 0. So from here we get k1 equals to 1 by 2 and k2 equals to 0, because we by convention take k1 is greater than k2. So now we have got two unequal value and which are, and difference is not an integer. Okay. Now we have solved this. Now what we need is, we need to find the recurrence relation. Recurrence relation. Now for finding recurrence relation, what we have to do is, we have to equate the coefficient of x to the power x to the power n plus k, that is this entire term, equals to 0. Plus k has to be equated to 0, and here n can be written 0, 1, 2, 3 and so on till infinity. So what will the coefficient, what is the coefficient of this term? N plus k plus 1 to 4 n plus k plus 1 what do we have is okay, now we have minus 2, right, and this is Cn plus 1 plus Cn equals to 0. So this will give us the recurrence relation. So let's see what it is. N plus k plus 1 into 4 n plus k, this will be plus 4 minus 2, again this becomes plus 2. Cn plus 1 equals to minus Cn. So Cn plus 1 can be written as minus Cn over, let's take 2 common. This is not 2 and multiply with 2 with this 2n plus 2k plus 2, and what will that mean? 2n plus 2k plus 1, right? So this is what is called as recurrence relation. Now once we have got the recurrence relation, now we can convert this coefficient into the series form. So first let's solve for k1, because we will get two series solution. One which is corresponding to the value of k1, which is 1 by 2, and the other which corresponds to the k2 value, which is 0. So first solve for k1, which is 1 by 2. So substitute over here, what we will get is Cn plus 1 will be minus Cn over, this will become 2n plus 2 into 1 by 2, which is 1 plus 2. So it becomes 3, 2n plus 3, and similarly this becomes 2n plus 2, right? Now we can substitute n equals to 0, 1, 2, 3 and so on, and get the series for the first solution. Okay, so if we substitute n equals to 0, we will get C1 equals to minus C0 over 3 into 2. Now this is minus C0 over 3 factorial, right? If we substitute n equals to 1, we will get series as C2 equals to minus C1 over 5 into 4. And if we replace C1 by this, what will this be? Plus C0 over 5 into 4 into 3 factorial, that is 5 factorial. Similarly, if we replace n equals to 2, C equals to 3, C3 will be minus C2 over 7 into 6, which will become C2 is C0 by 5 factorial. So this is a minus C0 by 5 factorial into 6 into 7, that is 7 factorial, and so on. Okay, you can write it like this. So for n equals to any value r, what we can write it as C of r equals to minus 1 to the power r C0 over 2 r plus 1 factorial. Okay. So we can write one solution as y1 of x goes to x to the power k is 1 by 2 here, into summation n equals to 0 to infinity Cn, that is the coefficient, minus 1 to the power n over 2n plus 1 factorial into C0. So C0 is any arbitrary constant. Okay. And we can give it any value we want. So let's take C0 as 1. So this is x to the power 1 by 2 summation n equals to 0 to infinity minus 1 to the power n 2n plus 1 factorial. C0 we have chosen is 1, and we have x to the power n plus k. K is 1 by 2. So this is the first series solution. Now we have to find the other series solution. So similarly, we have to solve for the other value of k, which is 0. Okay. Now if we just replace k as 0, the recurrence relation Cn plus 1 was minus Cn over 2n plus 2k plus 2. 2k will be 0, so we just have 2n plus 2. Similarly, here we will have 2n plus 1. Now we can substitute n equals to 0, 1, 2, 3 and so on. Okay, this and get the second series. Okay. So for n equals to 0, we have series C1 equals to minus C0 over 2 into n. For n equals to 1, we have C2 equals to minus C1 over 4 into 3. And this can be written as C0 over 4 factorial. For n equals to 2, we can write C3 as minus C2 over 6 into 5. So this becomes minus C0 over 6 factorial. And in a similar way, when n equals to r, we can write C r equals to minus 1 to the power r C0 over 2r factorial. Right? Therefore, y2 of x can be written as x to the power 0 summation n equals to 0 to infinity minus 1 to the power n over 2n factorial. C0 we have chosen as 1, so this becomes x to the power n. So this is our second solution. So the general solution can be written as y of x equals to c1 y1x plus c2 y2 x. The main solution will be a linear combination of any of these two series solution y1 and y2, where c1 and c2 are arbitrary constants. Okay. Any doubts? Okay. If not, then we will close the session here, and I hope you are understanding something, and let's see you in the next week at the same time, Friday 6 p.m. and in that tutorial session we will do one more problem of Frobenius series solution only, where we have the equal roots. Here we got k as 1 by 2 or 0, and we will see a problem where both k1 and k2 are equal, and how do we find the solution for that. Okay, see you next week. Thank you.